students. Today we are going to discuss the interference of light and the conditions required to obtain such an interference pattern. The interference of light can be defined as the phenomenon of redistribution of light energy due to the superposition of light waves from two or more coherent sources. And from this interference we obtain alternate bright and dark regions or bands, and they are called interference fringes. So as shown in the figure, when two coherent waves coming from two different directions, that is from this direction and this direction, here in this region we get the superposition of the two waves, we get an interference pattern. And in the pattern, we have alternate bright and dark regions. See, the red arrows show the bright regions and the blue arrows show the dark regions. They are alternate in nature. Okay, so as a result, if we place a screen there, we get a pattern as shown here. That is, we get a pattern of alternate bright and dark bands on the screen. Now, at the bright bands, the two waves will be in phase and they will produce constructive interference. So, the two waves as shown in the figure here, the two waves in phase will produce a resultant wave as such, that is double in amplitude. The phase difference between these two waves are, as you can see, is 0. Okay. Now at the dark bands, two waves that are out of phase will produce regions of destructive interference. And here we have two waves that has a phase difference of pi, right? They have a phase difference of pi, hence they are out of phase and they will superpose to produce a resultant wave of darkness, of no intensity, of low intensity. Okay, hence we get alternate regions of bright and dark regions in the interference pattern. Now, there are certain necessary conditions to produce sustained interference. Those are stated here. Let us read through it. The sources must be coherent. We can have two or more sources. All the sources must be coherent. The next one, amplitudes of the interfering waves should be equal. Only then we'll get the maximum amplitude in the constructive region and the minimum amplitude in the destructive region. Next is the separation between the sources must be small. That is, the sources from which the light is emerging, the two interfering waves are emerging, the distance between those two sources must be very small. Now, the next is the separation between the source and the screen on which we are viewing the pattern. That should be very large. Now, the state of polarization of the interfering waves should be same. And the interfering waves should propagate in the same direction. They should not go in the opposite direction. They should interfere along the same direction. The next point is that the sources must be narrow. That the source must be very small. Now, in this conditions, we came across a term that the source must be coherent. Now, what do you mean by coherent light? Two waves are said to be coherent if they have the same frequency or wavelength, they have the same amplitude, and they maintain zero or a constant phase difference between them. This definition is very important. You have to understand each and every word of it. Okay, everything is important in it. So two waves are said to be coherent if they have the same frequency, they have the same amplitude, and they have a zero or constant phase difference between them. Now, two independent sources can never be coherent. Okay. Some examples for coherent sources are two slits which are illuminated by a common monochromatic source of light. By monochromatic we mean that its wavelength is the same, or it has a single wavelength, single chroma, single color. Okay. Now the next example is we can use a source light and its reflected light as two waves to interfere. Okay. Now the next example is we can use the two refracted light rays from a same source. They can be made to interfere and produce interference pattern. Okay. Here in the lab, coherent sources are the sodium vapor lamp and the lasers. Now this animation shows the nature of coherent light. Here you can see that we have a beam of light rays. Okay, they have the same frequency, right? They have the same amplitude, right? And the phase difference between these rays are 0. Okay, that is when we look at the crest of one wave, we see the crest of the other wave also. Exact same point. Okay, so the phase difference between all these waves are 0. Now, to obtain coherent waves, one of the techniques used is we can use a double slit. So in this double slit experiment, what we do is that we have a common source, and from that common source, light is propagating towards the slits, and from these two slits, we have two separate sets of waves emerging. These two separate sets of waves, they interfere and produce such an interference pattern on the screen shown by the whiteboard. Now, let us compare these set of waves. Here, the image on the top shows a set of beams having the same frequency, they have the same amplitude, and their phase difference between them is 0. So they are coherent waves. Now in the set of beams in the middle, they also have the same frequency, they have the same amplitude, but they maintain a constant phase difference with each other, right? You should see the relation between two waves alone. So if you compare the black and the red wave, they have a constant phase difference of 0, right? Now if you compare the pink and the black wave, they have a constant phase difference of pi, right? So they maintain a constant phase difference, hence these set of beams are also coherent. Now on the beam of rays shown at the bottom, here the waves do not have a constant frequency. They don't have a constant amplitude. And also the phases. Here the phases are almost constant, but again the phase may be constant or may not be constant. So they represent a beam of incoherent waves, or that shows incoherent light. So what is incoherent light? From the definition we can say that two waves are said to be incoherent if they do not have the same frequency, same amplitude, or maintain a 0 or constant phase difference between them. If they do not satisfy the conditions, then those waves are said to be incoherent waves. Now, two independent sources are incoherent, and examples are tungsten filament and a fluorescent bulb. Okay, so these beams are representing incoherent light. Now let us go through the necessary conditions to produce sustained interference again. So these are a set of coherent waves. So the sources that are interfering must be coherent. The amplitudes of the interfering waves must be equal. The state of polarization of the interfering waves must be the same. The interfering waves should propagate in the same direction. The separation between the sources must be small. Here in this figure, you can see the screen with two slits, and monochromatic light is falling upon a screen with two slits. So light then emerges from the slits as two different waves. Okay, and these waves interfere to produce an interference pattern that can be viewed on the viewing screen. Okay, so first let us see the separation between the sources. So on the screen we have two slits, and the separation between them is usually of the order of millimeters or microns. Separation between those two slits is very small. Okay, it should be very small. Now the separation between the sources and the screen must be large. So here from the slits, the viewing screen is placed farther away. Usually it is placed at distances of meters. Okay, so as you increase the distance, we can magnify the interference pattern. Now the sources must be narrow. It means that the thickness of the slit, each slit has a finite thickness, right? That should be very small. It is usually of the order of microns. Okay, so a pinhole, a hole produced by just poking a pin on a paper, can act as a source of light. A pinhole can be a source of light, or a vertical slit. Here we have shown a horizontal slit. It can be a source of coherent light. Here take notice that our slits are placed horizontally. Hence, we get the interference pattern of horizontal alternate bright and dark fringes. Okay, keep this in mind. So in practice, we use such a setup. Here we have a helium neon laser emitting red light. It passes through slits of very small dimensions, okay, and produces an interference pattern placed on the screen. So on the screen you can see a bright central spot, and around which there are alternate bright and dark fringes. That's all for today. Thank you.